So we know that if you put sodium chloride into water, that it will separate into its ions or ionize in order to dissolve into the water. Well, not all ionic compounds are going to be soluble in water. And so if you take two ionic solutions and you mix them together, sometimes an insoluble substance will form, and that's called a precipitate. So if you mix two aqueous solutions together and you have a solid that forms, it falls out of solution as a precipitate. Solubility is really difficult to predict from a formula, but based on experimental data or observational data, we can come up with some solubility rules that help us identify whether an ionic compound is soluble or is not soluble. There's a list of these rules, but I will also show you a chart that you can use and reference when you're looking at solubility. But in general, there are general rules that help you remember. All group 1A salts, all ammonium salts, so that would be your NH4 plus salts, and nitrate salts, NO3 salts, are going to be soluble. And so those are your NAGs, your ammonium, nitrate, and group 1A salts. So here's a table of the solubility rules, and what you can see is that you're going to be able to look on here and say, okay, I have fluoride, anion, and ammonium as my cation, and together those are going to be soluble. So they will dissolve in water and become ions in water. However, anything that is in green is going to be insoluble. So you see that if you look at ammonium salts here, all of these are soluble. That was one of our rules, right? We also had our group 1 metals, for the most part, are going to be soluble. There are just a couple of exceptions, and that's the phosphate here, lithium phosphate, and lithium fluoride is slightly soluble. Otherwise, all of your group 1 are going to be soluble. And then we had nitrates, and that would be this group down here, and you can see that all of your nitrates are also soluble. So those general rules do apply here. I'm going to try to get rid of some of these arrows that I've drawn on this page. Okay, so the green ones are going to be what's insoluble, and you can see that most of the phosphates are going to be insoluble. So mostly phosphates are going to be insoluble. Lead, for the most part, is going to be insoluble. There are some solubles, but for the most part, it's going to be insoluble, along with silver as well. You can see that a lot of hydroxides are also going to be insoluble, and carbonates are also going to be insoluble. So you start to see some patterns when you look at this solubility rules chart. Once you recognize those patterns, you should write them down so that you have a general guide for what is going to be soluble and what is going to be insoluble. So as said before, not all ionic compounds are going to be soluble in water. So if you take two solutions of soluble ionic compounds and you mix them, it's possible that a new compound will form. And that type of reaction we've always called a double replacement reaction. You might also see it called a metathesis reaction or an exchange reaction. But when you have this exchange of ions and a solid is produced, that is called a precipitate. Okay, so here we have these double replacement reactions where we have two ionic compounds that are being combined together, magnesium nitrate and sodium hydroxide, and they are switching partners. So now magnesium is bound with hydroxide and sodium with nitrate. And using our solubility chart, we can see which one forms a solid. Now our reaction here is showing us that this is a solid and that our magnesium hydroxide is going to form our precipitate. That is going to fall out of solution as a solid. So you can just tell by the state of matter from an equation which one is going to be the precipitate. However, at some point you also need to be able to determine that if there is an ion exchange, what is going to stay in solution, what is going to be soluble, and what is going to be insoluble. And that is where you use the solubility table and your solubility rules. So there are multiple ways that you can write double displacement reactions. The form that we've been looking at so far is called the molecular equation, and that is the equation that gives the overall reaction with the formulas and stoichiometric coefficients. And so it really tells you the overall reaction of having an aqueous solution of calcium nitrate plus sodium hydroxide, 2 moles of that reacting in order to give you a precipitate of calcium hydroxide plus 2 moles of sodium nitrate. And it can be really helpful, but a more accurate representation of what's happening is the complete ionic equation. So in a complete ionic equation, it's going to show all of the ionic compounds as they separate out into their aqueous environment, so as they would be in the solution. So if we start with calcium nitrate, we can see that it's going to separate out into a calcium 2+ ion and 2 nitrate minus ions. That's what it's going to dissociate into when it is dissolved in water. We also can see that we have sodium hydroxide. Now remember, our balanced equation told us that we had 2 moles of sodium hydroxide, which means we're going to have 2 sodium ions and 2 hydroxide ions. On the other side of the equation, on the product side, we have calcium hydroxide, and it's a solid. Since it's a solid and it's not an aqueous, it's not going to separate into its ions. It's going to actually be a solid. So that doesn't separate out into ions. And then you would have 2 moles of sodium nitrate, and that's aqueous. So that means that we're going to have 2 sodium ions and 2 nitrate ions. Okay. So if we write out the complete ionic equation, we are going to write out Ca2+. So we're going to write out our reactants here in their ionic form. And we're going to write out our products in their ionic form if they are ions. If they're solids, we keep them as a solid. Okay? So we put them all together into one equation, and that's called the complete ionic equation. So anything that's aqueous that you have an AQ next to is going to separate out into its ions. Anything that's an S or an L or a G, those do not form any ions, and so you would just write them as the compound. So one thing you should notice is that it stays balanced if the compounds are dissociated properly. And so you can see that you're going to have 2 NO3 minuses, 2 Na pluses, and then your 1 calcium ion and 2 of the hydroxide ion. So it stays balanced for you. Also notice that some ions appear in the same way on both sides of the arrow. So here we can see that we have both the nitrate ion appears both ways, and the sodium ion appears the same ways. And if it appears the same on both sides of the equation, it's called a spectator ion. Spectator ions. They appear on both sides of the arrow because they don't participate in the reaction. So they're like spectators at a sporting event. They're just watching it happen. They're not participating. So do not participate in the reaction. If the spectator ions are removed, only the essential reaction remains, and that is called the net ionic equation. So a net ionic equation is where you are crossing out anything that doesn't change from the left side of the equation to the right side of the equation. And anything that doesn't change, any of the ions that don't change are spectator ions. When you cross them out, you end up with a net ionic equation. The only reactants that form the product an insoluble salt in a precipitation reaction. And so here we would have calcium plus 2 hydroxide ions are going to combine to form the precipitate of calcium hydroxide. So you should notice again that the equation stays balanced. The net ionic equation can be used to summarize large numbers of similar equations. In this case, any soluble compound containing a calcium ion will react with any soluble compound containing a hydroxide to form an insoluble calcium hydroxide. Oops. So let's do a little bit of practice here. We're going to write ionic and net ionic equations for the following reactions that we have here. So let's look at this first reaction. We're going to write it up here. We have zinc with a solid, and so that's going to stay as a solid. We have aqueous hydrochloric acid, and we have 2 moles of it. Hydrochloric acid breaks off into hydrogen ions and chloride ions, and we have 2 moles of each, so we're going to get 2 of each of those. That is going to react to form zinc chloride, which is aqueous. That is going to separate into ions of zinc 2 plus and chloride ions of minus. And we have 2 chloride ions here. And we have hydrogen gas, which is a gas, and so it doesn't form ions. All right, so this is going to be our ionic equation. Our net ionic is where we cross out any spectator ion. So what appears the same on both sides? Well, to me, it looks like chloride and chloride appear on both sides. So we're going to cross those out, and we're going to get a net ionic equation of zinc solid plus 2 hydrogen ions are going to react to form zinc hydrogen ions plus hydrogen gas. I'm going to cross this out here, and we're going to do this next one down here. Okay, we have zinc solid, and it's going to react with copper nitrate. So we have copper, it's aqueous, so it's going to separate into ions, plus 2NO3 minus. It's going to react to form, we got an aqueous, so that's going to separate out into ions, plus and we have a solid copper. Okay, so this is our ionic equation. We're going to look for whatever appears on both sides in the same form. Looks like this. This appears on both sides in the same forms, the nitrate. So that's going to be crossed out. And our net ionic equation is going to be all right. And why don't you try the last one? All right, so pause the video if you need to finish it up, and then the answer will appear on the next slide. And here's your answer. We have our ionic equation and our net ionic equation.